Example 30 is an error analysis question. We have a triangle ABC that has a perimeter of 45 units. So here's my triangle ABC. I'm told AB is 4x. I'm told BC is 5x minus 5, and AC is just x. Right? The perimeter we know is 45. What does that mean? That means all of these have to add together to equal 45. Perimeter is the sum of your side lengths. Okay, and Jenny says that after solving for x here, she's determined that this is an equilateral triangle, which is incorrect. Let's figure out why. Error analysis. All right, let's combine our like terms here. We got 4x plus x plus 5x, that's 10 x's. So 10x minus 5 equals 45. Get that 10x alone by adding 5 to both sides. That'll give me 10x equals 50. I can divide both sides by 10 here to get x equals 5. Okay, what does that mean? I know x is 5. I can plug that into the sides now and figure out how long they are. So AB, for example, was 4x. So 4 times 5, since 5 is what we got for x, gives me 20 for AB. Okay, what about BC? Okay, BC is 5x minus 5. Okay, well again, I got 5 for my x, so I'm plugging that in. 5 times 5 minus 5. Okay, 5 times 5 is 25. 25 minus 5 gives me 20. All right, so far Jenny's theory is still good. AC though is just x. And x is 5, so that means AC is only 5. So we only have 2 congruent sides. So Jenny was wrong calling it an equilateral, because equilateral, all the sides are congruent. Instead, we have an isosceles triangle here with 2 congruent sides. In example 31 here, we're filling in some blanks about parallel lines and some angles formed by the transversals. So we're talked about here angles PQR and QHJ. So PQR is that 32-degree angle. If I highlight P to Q to R, it's this. The angle is the interior of those sides that I highlighted. Again, that other angle was QHJ. So if I'm highlighting from Q to H to J, that's this angle right here. So we're talking about the angles where I have my blue highlights right here. In this question, or the blanks that we're trying to fill in here, these angles are something because they are some kind of angles. So this is going to be a characteristic of the angles. This is going to be the name of the angle pair. Okay, well, on parallel lines, these angles that are in like matching corners of the intersection, like notice these are both in the bottom left of their intersections, the bottom left of H, the bottom left of Q. We call those corresponding angles. And on parallel lines, which we're told these are, corresponding angles are congruent to each other. So the blanks here are, these angles are congruent because they are corresponding angles. Corresponding angles. So the last thing is the measure of QHJ is, well, again, congruent to the other angle, which was 32 degrees. Congruent means equal in measure, so QHJ is also 32 degrees. In our next example, we have to solve for x and y. Students are really quick to point out vertical angles. So if you identify these as vertical angles, it's awesome. Vertical angles are always congruent. The problem here is I can't set up an equation using the vertical angles because they have different variables involved here. I can't do 4x plus 10 equals 2y minus 30 without a systems of equations, which is possible, but it's not a level of math that we need here for geometry. Instead, we need to find linear pairs. Okay, we have a linear pair right here. Those two angles are side by side on a straight line. A straight angle is 180 degrees. Therefore, that 4x plus 10 plus the 13x has to add up to 180 degrees. And I can absolutely solve for x with this algebra. Combining like terms here gives me 17x's plus 10 equals 180. Can subtract that 10 from both sides to get 17x equals 170. And I can divide both sides by 17 to get x equals 10 degrees in this problem. Now I could absolutely plug in that 10 now and use vertical angles to solve for y, but I'm just going to look at the other linear pair that I can solve here, which involves both of my y's. There again, side by side on a straight angle, these have to add up to 180 degrees. We also are going to see some unique algebra involved as we do this. So the 2 times the y plus 25 plus the 2y minus 30 has to equal 180 degrees. And hopefully you recognize you got to distribute here. 2 times y is 2y, 2 times 25 is positive 50, plus the 2y minus 30 equals 180. After taking care of parentheses, we can combine like terms. 2y plus 2y, 4y's. Okay, 50 minus 30, plus 20. Now we can continue with our algebra to get y by itself. We're going to subtract 20 from both sides. That gives me 4y equals 160. Then I can divide both sides by 4 there to get y equals 40 degrees for this problem. Our next example is a review of some trapezoid properties. We have a select all that apply for true statements. You might have a hard time seeing these options here, so I'm just gonna zoom in and out so I can see the figure. Option A says AX is congruent to BY. Okay, here's AX, here's BY. They have dashes on them, but not the same amount of dashes. Congruent things have to have the same amount of marks on them to be congruent to each other, so that is not true. The next one says dx is congruent to cy. Okay, here's dx, here's cy, same problem. Dx has 2 dashes, cy only has 1 dash. We need the same amount of marks to be congruent, so that's not true. Next says xy is parallel to cd. Okay, xy is right here, cd is right here. This is an interesting one. Because of the marks on the sides, we know that xy is called a mid-segment. Mid-segments connect to the midpoints of the legs here on our trapezoid. And mid-segments are indeed always parallel to these sides that they don't touch to the bases of our trapezoid. So not only do we have one pair of parallel sides here, A, B, and C, D, mid-segments will also be parallel to both of those sides. So that statement is absolutely true. That is one for us to circle. The next one says that xy is half of AB plus CD. So that green is half of AB plus CD. This is true. This is how you find the length of a midsegment on a trapezoid. It's just the average of the bases. So whatever this is plus whatever this is divided by 2. The same thing as 1/2 of the sum of those two measurements. That is absolutely true. And then last we're told that trapezoid ABYX is congruent to trapezoid XYCD. Or they're essentially saying in that one is that this trapezoid is the same as this trapezoid, that they're congruent to each other. And the problem in that, even though we have a lot of pieces that would match each other, like this angle being congruent to that angle D, like these angles being corresponding angles, the problem with it is the length of these two sides. They cannot be the same. It would not be a trapezoid. The parallel sides are not congruent to each other on a trapezoid. So that would not be true in this statement, only C and D. In example 34, we have some true or false. First example, true or false, angle INM is supplementary to angle KNL. INM, KNL. These angles are not adjacent on a straight line. There is no evidence that one of them is 90 degrees, that the other is 90 degrees. False. These do not add up to 180. There's no evidence of that being true. Next says angle INJ, that would be this angle here, is congruent to angle MNL, this one here. It says because they are vertical. It's absolutely true. Those are vertical angles that are congruent to each other. That is a true statement. The next one says angle MNL, that's this angle, plus LNK, that is this angle, plus KNJ, that's this angle, equal 180. Absolutely true. Those three angles are on one side of a straight angle. They have to have a sum of 180 degrees. Our next one says angle JNI, that's this angle, plus angle INM, that's this angle, equals 180, which is true, but because they are vertical is not true. Those are not vertical angles. They do add up to 180, but not because they're vertical, because they're not vertical. That's a linear pair, not vertical angles. That is false, not a true statement. Lastly, KNL is 90 degrees. So KNL is this angle right here. Is that 90 degrees? Well, here's a straight angle that I need to know, or I have to know, is 180 degrees. And on the other side of KNL, we have a right angle, a sum of 90 degrees. So yeah, that has to be 90. Because on this side of the straight angle needs to be a total of 90. So if there's 90 all the way to this side in K, there needs to be another 90 degrees that does have to be a right angle there. That is a true statement. Question 35 is a tricky one for some students because it talks about coordinates, it doesn't give you a graph. You have to understand what it's asking you for. It says that there is a house that belongs to Ashley located at 9-3. There's a pizza shop that's located at 6-7. And we need to find the shortest distance from the house to the shop. Well, the key word there is distance. This question is just asking us to do a distance formula with the coordinates that are involved here. I'm gonna label the house as x1, y1, the 9 and the 3, the pizza shop as x2, y2, and I'm gonna plug those into my distance formula. The square root of x2, 6, minus x1, which is 9, plus, that's squared, plus y2, which is 7, minus y1, which is 3, squared. Parentheses first, 6 minus 9 is negative 3, 7 minus 3 is positive 4, exponents next, negative 3 squared is positive 9, 4 squared is 16, 9 plus 16 is 25, and the square root of 25 is exactly 5. So each coordinate here was a mile, 5 miles between the house and the pizza shop. Our next question is asking us to recognize a type of transformation that has occurred on each of these graphs. We got 4 of them to look at. Let's zoom in on our first one. What I see here is symmetry, mirror images. Like if I got the midpoint between B and E, it'd be right there. The midpoint between C and F is there. The midpoint between A and D is there. Therefore, what I have is a flip over the line that connects all those midpoints because I can connect them with a straight line like this. So that's just a reflection over the y-axis. This didn't ask me for the specific rules, but I'll tell them to you anyways as we go through. This is a reflection over the y-axis. And our second graph, what I see is my points A, B, and C, my blue triangle over here, just shifting this way. This is a translation, a slide. This is specifically going from, it's hard to read these numbers here, I think that's a positive 1 for the x-coordinate there and a negative 7 here. So that's left 8 units, my y's are at 2 and negative 1, so it's left 8, down 3. All those points are sliding to the left 8 and down 3. That is a translation, a slide, okay? Whoa, on this one, our figures are not congruent, right? There's clearly, our image here is way bigger than our pre-image. That can only happen with a dilation. This specific one, let's see, that side that was 2 units long became 6 units long. That's a dilation with a scale factor of 3. That triangle is 3 times larger. And then lastly, what I'm seeing here from pre-image to image is this triangle just turning around the graph. And turns are rotations. Okay, a few ways I could describe that. If I'm only moving 1 quadrant clockwise, that'd be 90 degrees clockwise. If I think about it counterclockwise, that's going 1, 2, 3 quadrants, that'd be 270 counterclockwise. In question 37, we're asked to provide a counter example to a false conjecture. So Kyla claims that the interior angles of any polygon must be 360 degrees or greater. If you're in your second semester of geometry, you better know that the angles of a triangle only add up to 180 degrees. So a triangle is a counterexample that proves that that statement is false. In example 38, we have to solve for the measure of angle AOD. So that's this angle here. If we knew the measure of this angle, we could get that pretty easily. So I need x. I need to figure out what x is and plug it in there. How can I do that? Well, I can do that knowing the properties of straight angles. Very important. We've seen it in a few problems already. Straight angles have 180 degrees on either side of them. So all 4 of those need to have a sum of 180. So 60 plus 3x plus x plus 10 plus 2x plus 20 has to equal 180 degrees. Algebra. Like terms here, 3x, 1x, 2x, that is 6 x's. 60, 10, 20, that is 90 when I add those together. It's combining like terms. Now I get that 6x alone by subtracting 90 from both sides. Gives me 6x equals 90. I can get x alone now by dividing both sides by 6. And that gives me that x is 15 degrees. Okay, so I need to sub that in now, right? I gotta figure out how many degrees that angle is in order to get angle AOD. So that's angle COD there where the 3 x's. And COD is equal to 3 x's. So 3 times 15 is 45 degrees. And now that I know that that is 45 degrees, I can get the measure of angle AOD with angle addition, 60 plus 45. So the measure of angle AOD equals 60 degrees plus 45 degrees. That is 105 degrees. Next, we're asked to write a sine and cosine ratio of two different angles. First, we need the sine of angle A. I like putting a little theta symbol where my angle is so that I can label my sides based off of that, okay? Remember, for sine and cosine, these are trig ratios. We want to label our triangles with the hypotenuse, the opposite side of our given angle, and the adjacent side of our given angle. Our hypotenuse is 17. It's the longest side. It's the side across from the right angle. Opposite of my theta would be the 8. That's my opposite. 15 would be the adjacent side. Hopefully you remember this acronym. SOHCAHTOA is how we can write our ratios. It's spelled SOH. That means the sine ratio is opposite over hypotenuse. That would be 8 over 17. For the cosine of B, we have to start this over because my sides are no longer going to be the same except for the hypotenuse. That's always the longest side across from the right angle. From the perspective of angle B, though, putting my theta at B, 15 is now the opposite side, and 8 is the adjacent side. 15 is the opposite of that given angle. So cosine, SOHCAHTOA, spelled with a C-A-H in the middle. That tells me the cosine ratio equals adjacent over hypotenuse. So that would be 8 over 17. Notice those are both the same. That's a very important fact. In any right triangle, the acute angles need to be complementary, and any angles that are complementary, the sine of one is equal to the cosine of the other. And one more time, we were asked for a tangent ratio, another trig ratio involved here of the 30-degree angle. So for trigonometry, we're labeling again our sides hypotenuse, opposite, adjacent. Our hypotenuse here would be 14 times the root of 41 because that is across from the right angle. Our opposite side of our 30 degrees would be the 7 times the root of 41, and then that last side there would be my adjacent side. SOHCAHTOA tells me the tangent ratio is opposite over adjacent. SOHCAHTOA, T-O-A is in there in the spelling. So the tangent of 30 degrees equals opposite over adjacent. So 7 times the root of 41 over 14 times the root of 41. In example 41 here, we're asked to find the scale factor of a dilation and then to write the dilation in function notation. So first, scale factor is just the image over the pre-image. This is a ratio comparing image and pre-image. Some measurement from the new shape compared to the corresponding measurement of the original shape. So as we look at a figure like this, we can use several different measurements. I like looking for sides that I can count. For example, on the image, AB prime there I can count is 6 units long. On the pre-image, the corresponding side AB is 2 units long. So my scale factor can just be those in a ratio, 6 to 2, and 6 over 2 is equal to 3. So scale factor 3, meaning that image is 3 times larger than the pre-image. Those points are also 3 times further from the origin than these points are on our pre-image. The scale factor then, the function notation then, would just be saying that our coordinates were multiplied by 3. So that would look like this. xy would become 3x, 3y. Example 42 here is really testing our knowledge of scale factors. It says we have a kite that is dilated with a scale factor between 0 and 1 to create another kite. And it's asking us on our image, the new kite, we have to determine if the perimeter is going to be greater than or less than, or what's our order here? We're determining if the perimeter of kite A is greater than or less than the perimeter of kite B. So we started with A, and we are multiplying it by a scale factor between 0 and 1. Multiplying it by something between 0 and 1 to end up with kite B. Well, something between 0 and 1 would be a reduction. If the scale factor is less than 1, that shape is going to get smaller. So that means B is smaller than A, so the perimeter of kite A would be greater than the perimeter of kite B. Example 43 is a partitioning question. We need to find a point that's going to partition a segment into a ratio of 2 to 3 with our endpoints given here at A and B. Remember, the first key to a problem like this is finding the distance between the coordinates for A and B. It's a directed segment, it's named with A first, so that's going to be my 1's when I label this. X1, Y1, these will be my 2's, X2, Y2. And I'm labeling these so that I can find the distance in coordinates, and that is found with the slope formula. That'll give us the distance between the Y's and the X's. So that's Y2 minus Y1, 3 minus negative 2, over X2 minus X1, negative 11 minus 4. 3 minus negative 2 is positive 5. Negative 11 minus 4 is negative 15. What are these numbers? These are how far apart our X and Y coordinates are. So our Y's are 5 units apart, our X's are 15 units apart. It's a positive 5 for the Y's, negative 15 for the X's. That's the total distance from end to end. Our point, though, is only going to be some fraction of this distance away from that starting point of A. And we find that fraction from this ratio. This is saying 2 parts before the point, 3 parts after. So it's splitting the segment into a total of 5 parts with, again, 2 parts before it. So our point needs to be 2/5 of the distance from A to B. So I need 2/5 of these distances. So I'm going to multiply here by 2/5, both of these values. When I do 5 times 2/5, I get positive 2. When I do negative 15 times 2/5, I get negative 6. Now I need to remember that came from my Y coordinates. This came from my X's. So my new Y coordinate of my partitioning point is going to be positive 2 units away from the Y of the starting point. My new X coordinate will be negative 6 units away from the X of my starting point. So A was our first point, our starting point of this segment. Then again, the negative 6 came from the X's, so I'm subtracting that from the X coordinate of 4. 2 came from the Y's, I'm adding that to the Y coordinate there, and that leads me to this partitioning point, which would be located at negative 2, that's 4 minus 6, negative 2, and then 0. Negative 2 plus 2 gives me 0. That is my partitioning point. At example 44, we're writing some more trig ratios, and then we're actually going to be solving for measurements using trigonometry. So we're asked to write the sine, cosine, and tangent of 2 angles, starting with angle WXY. So WXY in our triangle here would be this angle here at X. So I label my sides. That's my hypotenuse. This will be my opposite side. This will be my adjacent side. And I can write my ratios from here using SOHCAHTOA. That acronym tells me how to write ratios. So that starts with SOH. The sine ratio is opposite over hypotenuse. For this, that would be 8 over 17. So my sine ratio for this angle is 8 over 17. Right, the next 3 letters in SOHCAHTOA tell us about the cosine ratio, CAH. Cosine is adjacent over hypotenuse, so 15 over 17 would be my cosine ratio for this angle. And then our tangent ratio, those last 3 letters of SOHCAHTOA, TOA. Tangent is opposite over adjacent, so 8 over 15, right? Next, we need to do the same ratios, but we're doing them for the other acute angle in the triangle now, which is XWY. So for this angle now, and that is going to change how we label the 8 and the 15. The hypotenuse is still the 17 across from the right angle, but our opposite side now for this angle would be 15. That is opposite of our given angle theta. And 8 would be our adjacent leg. And now I can write, again, my sine, cosine, and tangent. So sine, SOHCAHTOA is opposite over hypotenuse. That's 15 over 17. Sine of this angle equals 15 over 17. The cosine ratio for this angle be adjacent over hypotenuse. 8 over 17. 8 over 17 for my cosine ratio. And lastly, tangent ratio is opposite over adjacent. So 15 over 8. Those are my tangent, cosine, sine ratios for both of the acute angles in that triangle. Part 2 is asking me to find the measure now of those angles, W and X, right? Using 3 letters here to name them. The measure of angle WXY, so that is this angle that we're solving for first. That is this angle here. We can use any of these three ratios to solve for the measure of that angle, right? For example, if I want to use the sine ratio, I would write this. The sine of, we can just call it W, angle W, or this is X actually, this first angle here, sorry. The sine of X equals, again, we have the ratio right there. We know it equals 8/17. Well, we've learned to find an angle measurement, we have to do inverse trigonometry. So if the sine of X is 8/17, then X is equal to the inverse sine of 8/17. Which is just something for us to calculate in the calculator, right? Inverse sine of 8 divided by 17. It's about 28 degrees if you're rounding to the nearest whole number. I like to tell my students to round to the nearest 10,000 for trigonometry, because some of those questions get a little tricky. So I got 28.0725 degrees for this measure. We could absolutely just use complementary angles now to solve for W, right? We know that this angle 28 point yada yada has to add with the other angle to equal 90 in the right triangle, or we can just again use another one of our ratios. Let's use the tangent ratio this time for angle W here to find this measurement. The tangent of W, that's supposed to be an N, sorry. The tangent of W equals, again, that ratio was 15/8. So equals 15/8. Well, if the tangent of W is 15/8, then W would equal the inverse tangent of 15/8. And we just need to calculate that. Inverse tangent of 15 divided by 8 gives me 61.9275 degrees. Our next two examples involve angle pairs on parallel lines with transversals. So we know we have parallel lines here because they have matching amounts of arrows. We need to be able to identify the special angle pairs. In this case, we have alternate interior angles. They're between the parallel lines on alternate sides of the transversal. On parallel lines, these alternate interior angles are congruent to each other. So if we want to solve for x, we just need to know that 8x minus 4 has to equal 60. We can add 4 to both sides here to get 8x equals 64. And we can divide both sides by 8 to determine that x equals 8 degrees for that example. Our next example is similar because again, we're going to have parallel lines here with an angle pair to identify. How do I know the lines are parallel this time? Because there's no arrows on them. Well, the directions say right there, line 1 is parallel to line 2. The angle pair we're looking at now is consecutive interior angles. They're in between the lines that are parallel, so they're interior. They're on the same side of the transversal. Sometimes these are referred to as same side interior angles. And these are always supplementary on parallel lines. So that means the 3x plus 20 plus the 2x has to equal 180 degrees. Supplementary things add up to 180. Right? Combining like terms, 3x and 2x gives me 5x's. Positive 20 still there on the left, equal to 180. I can get the 5x alone now by subtracting 20 from both sides. That gives me 5x equals 160, and then I can solve for x by dividing both sides by 5. Pretty sure that's 32. Let me double check. Yep, 32 degrees for x in this example. Chris, future me, edit this video. I messed up 40 from before. Go back and find that, delete that clip, and put this in instead. In this example 40 here, we have a special right triangle. It's a 30, 60, 90. I have 30 degrees, I have a 90. This would be 60 degrees down here in this corner. And I'm asked to find the tangent ratio of this. And if we're not careful, we would just use the two sides that were given to us here. But remember, the tangent ratio uses the opposite and adjacent side of our given angle, which is the 30. And that adjacent side is the blank one here. So we actually need to use the rules of special right triangles to figure out the measure of A. Now, if you don't remember the rules of special right triangles, you can always do Pythagorean theorem. Since I know two sides already, I can do Pythagorean theorem to find that third side and then do opposite over adjacent from there. But special right triangles would be a quicker way to do this. This would be our short leg because it's opposite of the smallest 30 degrees. And the rule is that the long leg is equal to that short leg times the square root of 3. So that adjacent side is equal to 7 times the root of 41 times the square root of 3. And the way that you would calculate that is by just multiplying the square roots together. So 41 times 3, we would have the square root of 123 in there. So that would be my adjacent side. And now I can write that tangent ratio of 30 degrees. Opposite over adjacent, so opposite was 7 root 41 over adjacent, which is 7 root 123. Example 47 is really testing our knowledge of rigid transformations because we have to look at all of these given here and determine which ones preserve side length, which means results in a congruent figure. That's what rigid transformations are. So as a reminder, the 3 rigid transformations are translations, reflections, and rotations. All right, and we see 3 of those written out for us right here, just plain English. It's rotation, translation, reflection. Those will absolutely preserve our side length. Then we have some function notations thrown in there. We just need to understand how this works. If you multiply coordinates by a number, you are enlarging it. If that number is more than 1, you're reducing it if that number is less than 1. So examples like that, function notation would make the shape bigger. So would this one, it would make the shape grow in size. And therefore those do not preserve side lengths because the side lengths are going to get bigger. I used the word enlargement before. Again, that makes a shape larger, so definitely not something that's going to preserve side length. Okay, dilations, those are the transformations that enlarge or reduce, that make them bigger or smaller. So that's going to change the length of our sides. That would not preserve side length. Then we have 2 function notations left to look at. This function notation just says x plus 5, so y coordinates stay the same, but we add 5 to our x coordinates. That is what a translation looks like in function notation performed. This just means sliding 5 units to the right. So that would not change the side lengths, that would preserve them. It would keep them exactly the same. And then the last one, sometimes we get a little mixed up when we start switching coordinates. This is a reflection here, option B. It's a reflection over the line y equals x when you flip your x and y coordinates. And again, reflections preserve side measure. If you're ever not sure what a function notation does, you can just use the graph scratch paper that's given to you for your assessments. You can graph your own shape and say, okay, what's going to happen to my points if I flip them? And you can see where the image would end up, and you'll be able to determine if you have a congruent figure or not, if those side lengths are the same or not, and they are preserved in option B. In option 48, it's almost the same question. This time, though, we're asked about angle measures. So which of these transformations will keep angles the same amount of degrees? Well, again, rigid transformations do not change our shape. They just move them somewhere else. The shape remains congruent. The angles included would be congruent. So remember, that's translations, reflections, and rotations. And again, we just have those. Rotation, reflection, translation. Those are all going to preserve angle measure. Remember, we talked about how some of these function notations were also these types of transformations. Like this one right here is a translation of just 5 to the right. Again, translations create congruent figures, including congruent angles. Angle measures are preserved. We talked about how option B was just a reflection over the line y equals x. That does not make the shape any bigger or smaller, doesn't change the angles. That will preserve angle measure. Okay, then we're getting now to the dilation options, the ones that are going to change the size of the shape. And this is where we need to understand that when we change the size of the shape, we're changing the side lengths, but the angle measures can stay the same. So dilations create similar figures. The sides grow proportionally, the angles remain congruent though. So angle measure is preserved in dilations. And enlargements are types of dilations. Those are the ones that make them bigger. And that last one, I, is an enlargement. It's taking your figure and multiplying it by a scale factor of 3. So it grows 3 times larger. That's side length, so not the angles. The angles are preserved. They stay the same. So actually the only one here that does not preserve angle measure is option D. The reason being is that the coordinates are not multiplied by the same value. So in a true dilation, we multiply the coordinates by the same value. This is an enlargement, a dilation of 3. They're both multiplied by 3. This has multiplied by different values, therefore the sides will grow wonky, the angles are going to change. That will not preserve angle measure. All right, we got a lot going on in example 49. We got 4 different lines. We have several true or false scenarios, we're being asked if there are certain angles here that are congruent based off of certain lines being parallel to each other. All right, so as we look at our first option, it says if R is parallel to S, then angle 1 is congruent to angle 15. Let's see where angles 1 and 15 are. Angle 1 is right here, angle 15 is right here. Those are alternate exterior angles, but it's important to know which lines are involved in creating those alternate exterior angles. Well, that one is at the intersection of line T and line R. That angle 15 is at the intersection of line R and line U. Notice how line S is not part of the creation of this angle pair. Therefore, R being parallel to S would not make angle 1 congruent to angle 15. It would have to be line T parallel to line U, making those angles congruent to each other. So that's really what we're being assessed on here, is the lines that we're talking about here being parallel, creating that congruent angle pair. All right, so we're gonna keep that up for all these examples. So next one, we got 1 and 5. Okay, 1's here, 5 is here. That's created by these lines. That is R and S. That would have to be parallel for these corresponding angles to be congruent. That is absolutely true in that example. Our next one is 3 and 5. Okay, 3's here, 5's here. Those are created by these 3 lines. Again, that is R and S. That would have to be parallel for those alternate interior angles to be congruent. That one is true. Our next one, we're looking at 13 and 3. 13 here, 3 here. Those would be alternate interior angles on these lines, T and U, not R and S. So that's false. Okay, next one, we're looking at 16 and 10. 16 is right here, 10 is right here. Those are created by these 3 lines. Again, that one works out. R needs to be parallel to S for those alternate exterior angles to be congruent. So that is true. Next, we have our last R and S true false here, which is involving angle 4 and angle 8. So angle 4 is right here, 8 is there. Those are corresponding angles on these 3 lines, which does include R and S. So yes, if R is parallel to S, then 4 is congruent to angle 8. Now we're switching it up. The rest of our options are looking at T and U. So our first one is regarding angles 11 and 5. There's 11, there's 5. Those are created by these 3 lines, alternate exterior angles on T and U. So absolutely, those are congruent on those parallel lines. Our next example is looking at 15 and 11. 15 here, 11 here. Those angles are created by these 3 lines. Again, that would be R has to be parallel to S for those corresponding angles to be congruent, not T and U. So that is false. Next, we have 9 and 7. 9 is here, 7 is here. Those are alternate interior angles on these lines. T parallel to U gives me congruent alternate interior angles, which is exactly what that statement says. That one's true. Next one, we have 1 and 15. Angle 1 is here, angle 15 is here. Those are alternate exterior angles on these lines. So if T is parallel to U, those are congruent. That is exactly what that option says. That one's true. Next, we have 7 and 10. I forgot to erase here. We got 7 and 10. So 7's right here, 10's right here. Okay, this is a tricky one. Those are created at the intersections of these lines, okay, which is T and U. However, those are consecutive interior angles, which are always supplementary on parallel lines. They're not congruent to each other, so that's false. They're only congruent if they're right angles. We don't have evidence of that in this example. And our last one, angle 16 congruent to angle 6. Angle 16 and angle 6 are not even on the same intersection of lines. Therefore, all kinds of false for that last one. Can't make that assumption that they would be congruent. In example 50, we're really being assessed on our knowledge of quadrilaterals and their individual properties. Okay, there's a little tree of quadrilaterals and all the shapes that are related to each other, and the tree can be very confusing. Okay, what's very important though is that we at least know the parallelogram tree. Okay, so there are several types of quadrilaterals. One type of quadrilateral that exists is called a parallelogram, where both pairs of opposite sides are parallel to each other. But then there are special parallelograms, like the rectangle and the rhombus, And then there's a very special parallelogram called the square, which just has all the properties of rectangles, rhombuses, and parallelograms. That's the main tree that we need to know. We need to know that all squares are parallelograms, that all rhombuses are parallelograms, all rectangles are parallelograms. Okay, from there I'll fill in the blanks with all of our other unique quadrilaterals as we look through here. Which of the following statements are true? All parallelograms are rhombuses. So it's trying to say that all of these have to be this kind of shape. But we know that's false because some parallelograms can be rectangles. Some of them can be squares, not just specifically rhombuses. So that is not true. Next, all kites are quadrilaterals. Okay, well, kites are four-sided shapes and quadrilaterals are four-sided shapes. So that's absolutely true. So here's something else we can add to our little tree here, right? Every kite is a type of quadrilateral. So this is a true statement because a kite has four sides. Next, all squares are rectangles. Ooh, this is an interesting one. Remember our tree, a square has all the properties of a rectangle. So it's a rectangle that also has rhombus properties. Okay, all squares absolutely are rectangles. And a way that you can think of this tree as I've written it here is every shape you see is the thing above it. So all squares are rectangles, all squares are rhombuses, all rectangles are parallelograms, all rhombuses are parallelograms, all squares are parallelograms, all parallelograms are quadrilaterals, all kites are quadrilaterals. That's the way we can read that there. So next says all rectangles are rhombuses. Yeah, all the rectangles are below. Rectangle is a special type of parallelogram. So that's absolutely true. Next, all parallelograms are trapezoids. This one messes our tree up and it makes it really, really confusing. So there's another type of quadrilateral called a trapezoid that has to have at least one pair of parallel sides. And parallelograms have two pairs of parallel sides. So by definition, they do have at least one pair of parallel sides. So yes, all parallelograms are trapezoids. It's absolutely true. Next, all parallelograms are squares. Again, no, it's the other way around. All squares are parallelograms. Some parallelograms can just be rhombuses. Some can just be rectangles. They don't all have to be squares. So that's not a true statement. And then lastly, it says all quadrilaterals are parallelograms. And again, our tree shows us that's not true. Some quadrilaterals are kites. Some are trapezoids. Some are just really ugly four-sided shapes. They don't have to be anything special with special rules to them, right? So that is, not true. Not all quadrilaterals are parallelograms. Example 51, everyone's favorite. We got a proof to go over here. We're given that segment KG bisects angle FKJ. And we're given that angles GFK and JHK are congruent to each other. Those are actually labeled there already for us. And that segments FK and HK are congruent to each other. Those are also labeled for us here in the proof. We have to prove that the two triangles seen here are congruent to each other. Okay, first off, given information. Boom, boom. That same stuff is mentioned right there. We know it's true because it is given to us. Next, we have another piece of given information. That first one right here, that KG bisects angle FKJ. It's given to us. It, however, is not labeled on the figure. So let's go ahead and do this. Remember, to bisect means to cut in half. Okay? So if KG, this segment right here, is cutting FKJ, this angle in half, what that means is that these two parts now, or halves, are congruent. They're equal halves. So we got to go in there and mark those angles congruent to each other. Let me do a better job of placing those marks so we can still see the congruent marks as well. Okay, those are congruent to each other. Again, that's given to us. All right, now the next thing that is stated in our proof is true because of the definition of an angle bisector, and I just kind of went over this, that those angles up here have to be congruent to each other because the bisector cuts that angle in half. So this angle right here is angle FKH. So we can say angle FKH is congruent to angle, and then we have the angle on the other side, this one, which we can call JKH. Angle JKH. These are congruent because a bisector cuts angles in half. And then lastly, we're saying the triangles are congruent. The most important thing in this proof is remembering that if you say triangles are congruent, the reason must be a congruency theorem, like side, 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 angle, side, and so on. Okay, and we have now, in this example, as we look at both triangles, we have two angles congruent for both triangles, and then in between the angles, we have sides that are marked congruent to each other. That gives us the angle-side-angle congruency theorem for those two triangles. In example 52, we're providing a counterexample for a false conjecture. Edna claims, if a quadrilateral has two pairs of congruent sides, then it must be a parallelogram. We're asked to draw and name a figure that proves to be a counterexample. So this is a false statement. Just because a shape has two pairs of congruent sides does not mean it's a parallelogram. There's a key word here that might have you confused right now. In a parallelogram, opposite sides are congruent to each other. So if you were to draw a four-sided shape where opposite sides are congruent, then yes, it has to be a parallelogram. However, there is a shape that exists where consecutive sides are congruent to each other. And you need to know that that is called a kite. That also has two pairs of congruent sides, but is not a parallelogram. Example 53 is another test of our knowledge of rigid transformations. So you tell this is going to be a point of emphasis for these big exams that we come into. Remember that reflections, translations, and rotations create congruent figures. When we perform those transformations, it does not change the size of the shape. It makes them congruent to each other. So we have here a select all that apply. It's basically asking us which of these results in a congruent shape, where we get one triangle to make a congruent triangle in a different place after transforming. Okay, so remember that can only occur when we translate, reflect, and rotate our figures. Any dilations are going to make a shape bigger or smaller. That will not result in congruent shapes. So we'll keep that in mind as we look at all of our options. Option A says there's a reflection and a rotation. The rules don't really matter here because reflections and rotations are rigid transformations. So it doesn't matter what line I flip over, how many degrees I rotate. If all I'm doing is reflecting and rotating, I will have a congruent figure when I'm done. So that's absolutely going to create a congruent triangle. Right? Option B says a 180 rotation. Again, that's a rigid transformation, followed by a reflection. So again, doesn't matter how amount of degrees we rotate or what line we flip over. Rotations and reflections are rigid transformations. They will result in congruent figures. Option C says dilation right away, boom, false. That can't work. Dilations make shapes bigger or smaller. They do not create congruent figures, okay? Option D says a reflection followed by a dilation. Again, dilation is going to make the shape bigger or smaller. That does not create a congruent figure. And our last option, we have a translation followed by a rotation. Remember, translations are slides. Doesn't matter how far you slide. Doesn't matter how many degrees we rotate. Those are both rigid transformations. Those will create congruent figures. Example 54 is really just assessing our knowledge on how dilations occur. The scale factor determines if a shape enlarges or reduces, gets bigger or smaller. However, you have a unique scenario where a scale factor can be a certain number and it creates a congruent shape that doesn't get bigger or smaller. And that's just simply when the scale factor is 1. Okay? Which is why in function notations that we see that don't have numbers in front of the x and the y, those are always rigid transformations, either reflections, rotations, or translations, because there's technically a coefficient of 1. So you can think of it, if you want to think of it as a dilation occurring, the scale factor is 1, so the shape stays the same size. It does not get bigger or smaller at all. Right? So if the scale factor was greater than 1, that would make the shape bigger, so not congruent anymore, but proportionally larger. And a scale factor of less than 1 will reduce the shape. Okay, so sizes are proportionally smaller. okay, but not congruent to the pre-image. K equals 1 though would keep the shape exactly the same. In example 55, we have a first example here going over special segments of triangles and their points of concurrency. Guys, this stuff, especially the point of concurrency, is just strict memorization. Can you memorize the special segments and the names of the points where they intersect each other? So as we look at the triangle, these are the three special segments that we're talking about here: CD, BF, and AE. They all intersect in the middle there at point O. In part 1, we're just asked what are these segments. The thing that gives away what they are the dashes on the sides. These dashes tell me that F is the midpoint of that left side AC, D is the midpoint of that right side AB, E is the midpoint of that bottom side BC. The special segments that go from a vertex to a midpoint are called medians. These are all medians. And the point of concurrency, where all medians intersect each other at, so that would be point O in this, where they meet in the middle, is always called a centroid. So in that figure, those special segments were medians because they go from a vertex to a midpoint, and where the medians intersect, we just need to memorize that point is called a centroid. In example 56, we have a trig problem. We have a right triangle with one side given, one angle given, and we have some other measures to solve for. We're gonna do this with trigonometry, right? So we start by labeling our sides. 30 would be my hypotenuse, it's across from my right angle. My opposite side is opposite of the acute angle given to us. So we have 36 here in this corner, so the opposite side would be this A over here. And then this would be my adjacent side. Let's try not to get those A's confused, right? That's just a variable. It could have been X, could have been any letter, right? Hypotenuse, opposite, adjacent. So we have a choice right now of what side we want to solve for first between A and B. It doesn't matter. I'm going to solve for A, okay? And I'm going to be using my sine ratio because I have the hypotenuse and I'm trying to find the opposite side. The O and H are used in the sine ratio. So the sine of 36 degrees will equal that opposite side of A, that's why I'm putting A there, not adjacent, but this opposite side of A over the hypotenuse of 30. When our variable is there in the ratio, we can just set this sine over 1, becomes a proportion now, which we can cross multiply and solve. 1 times A is A, and then we have the sine of 36 degrees times 30. And we just need to calculate that and be as accurate as we can as we're writing our answer down. So we have the sine of 36 degrees times 30, which is about 17, I like to round to the nearest 10,000 here, 17.6336 would be how long that is. Now I have two options from here of what I could do. Now that I know two sides, I could do Pythagorean theorem here with the b and say a squared plus b squared equals c squared. Okay, or I can just do trigonometry again to get the most accurate answer, because this is rounded now at this stage, right? So that'll give me an even more off answer here when I round for b at the end of a Pythagorean theorem. However, I could just do trigonometry now with my cosine ratio using my adjacent and my hypotenuse. And that'll give me the most accurate answer for b there. So now the cosine of 36 degrees equals my adjacent side of b over my hypotenuse of 30, and then we have the same setup here of cross multiplying. We get b equals the cosine of 36 degrees times 30, and we calculate that. Cosine of 36 times 30 gives me 24.2705 for the length of that leg. In example 57, we have an airplane taking off with an angle of elevation at 6 degrees. So this is our plane down here on the ground, beautiful plane. It's looking straight forward on the runway. It's gonna take off though and change its angle that it's moving at, right? So this is straightforward, that's the runway, but it's going to lift off like that, and it's gonna create an angle of elevation there. So we're told this angle of elevation is 6 degrees. And we're asked here, determine the altitude of the plane. So that would be how tall or how high it is in the sky, okay, after a horizontal distance of 10 miles. So this is representing our horizontal distance, the distance on the ground of 10 miles. So we can calculate this as a trigonometry problem, okay? Anytime you see angle of elevation, angle of depression, doing trigonometry to solve that. This will be my hypotenuse. X is opposite of that 6 degrees, 10 is adjacent. I have the adjacent, I need the opposite, so I'm ignoring the hypotenuse. I would be using the tangent ratio here. Tangent of 6 degrees equals opposite over adjacent. Again, we just turn this into a proportion, cross multiply and solve. 1 times x is x. Then we have the tangent of 6 degrees times 10. And the tangent of 6 degrees times 10 is equal to about 1.0510 miles. That's how high up that plane would be after 10 miles of horizontal travel if the angle of elevation is 6 degrees. Example 58 is a bunch of review of special segments and their points of concurrency. I'm going to go over a lot of information here. If you want better visuals to go for these segments, you can check out my Unit 6 videos. We're selecting all the accurate statements here. Altitudes meet at orthocenters. That is true. An altitude is a special type of segment. The point at which all the altitudes of a triangle meet is called an orthocenter. Perpendicular bisectors meet at incenters. That is not true. Perpendicular bisectors meet at a point called a circumcenter. Medians meet at centroids. That is absolutely true. Medians meet at centroids. Angle bisectors meet at incenters. That is also a true statement. Angle bisectors meet at incenters, which means they don't meet at circumcenters. That example is false there. F says perpendicular bisectors meet at circumcenters. That is a true statement. Circumcenter is a point of concurrency of perpendicular bisectors. Medians meet at orthocenters. Nope, we already said medians meet at centroids. That's not true. Altitudes meet at centroids. Nope, we already said they meet at orthocenters. Then our last three are about where these points can exist. Centroids can be outside of a triangle. That is false. All centroids are inside of triangles. Orthocenters can be outside of a triangle. That is true. Orthocenters are where altitudes intersect. Sometimes those are outside the triangle, specifically for obtuse triangles. Lastly, incenters can be on a triangle. That is false. This one should be easy to remember. An incenter has to be in a triangle. It can't be on a triangle or outside of a triangle. So A, C, D, F, and J are all the true statements here. The last several examples of our review here are all about constructions. Now I'm going to be going over these constructions very quickly. If you have not seen constructions yet, you should look up a different resource that breaks it down a lot slower, step by step how to do this. Now, in my experience, when you're assessed on constructions, you're not really assessed on how to do them by hand, but rather the steps that are involved or identifying what is being constructed by given some images of a construction. So mathopenref.com is a great reference, is a great resource that you can use to find videos that break down these constructions where you can play it one part at a time. Otherwise, I'm going over the basics here for it. The first constructions we're doing here is copying a segment. So we're going to make a segment that's congruent. I'm only going to do one of the three. If you have this packet for me, this resource, then you can practice extra. The way we're going to start by copying segment AB here is just drawing a segment that is clearly longer than AB. Okay, on that segment, we will label an endpoint. So over here, I can put a point. I can make that point C if I'd like. Next thing I'm going to do is I'm going to take my compass and I'm going to measure the length of my original segment that I'm copying. So the pointy part of my compass would go on one endpoint. The pencil would go on the other endpoint. I would try to get that measurement exactly. And then I would just carry that down here to my new segment. I put my compass on my endpoint C. I would make an arc through my segment, and I would label the intersection there of that segment. I'm going to label that point D, and that segment AB would be congruent to segment CD. The next construction we're going over is copying an angle. So I'm going to make an angle congruent to ABC. That starts with drawing a new ray for the first side of my new angle here. So there's my ray. I'm going to label this vertex here point D. I'm then going to take my compass and I'm going to draw an arc through my original angle. So my vertex would go, or my compass, the pointy part would go on the vertex of my angle. I would then lean the pencil down and I would draw an arc that goes all the way through the angle, like so. I'm going to keep the same measurement on my compass. I'm going to come down here to my new vertex for my new angle, and I'm going to draw an arc that's just as long, if not longer, than that one that I drew up there. Next thing I'm going to do is label some intersections. So I have two intersections up here now that I'm going to label. I'm going to label this point here, point E. and this intersection right here is going to be point F. This intersection right here will be point G. Next thing I'm going to do is I'm going to measure the distance between F and E, between those intersections on my original angle. So we would tighten up our compass. The compass would go on one point. The pencil on our compass would go on the other intersection. And then I would take that exact measurement. I'm going to carry it down here, put my compass on point G, and then make an arc that intersects right here. And I have another new point here. I'm going to call that point H. And the last thing I have to do to copy my original angle is draw a ray from my vertex through point H. So it looks something like that. Those would be congruent angles. Our next construction is going to be bisecting an angle. So we're going to be cutting angle ABC in half. Right? This starts similar to copying an angle. We're going to draw an arc all the way through this. So any setting we want, as long as it's not longer than one of the rays or the sides of our angle here, we're going to put our compass on the vertex, and we're just going to swing an arc that starts outside of our angle and goes all the way through. Let me try that again. There we go. Goes all the way through. Then we have some new points here that we're going to label. I'm going to call this one point D, this one point E, these intersections between my arc and the sides. We're then going to take a measurement on our compass that will allow us to make arcs here in the interior space between the sides of our angle. That mark can be out here, it can be really close, as long as it would be in between where these sides travel to. We're going to put our compass on point E. I'm going to have my compass about this setting right here. I'm going to put my compass on point E, and I'm going to make a arc with the pencil part of my compass right there in the interior. Then I'm going to keep this same measurement, the same setting on my compass. I'm going to carry it over to my other intersection, point D, and I'm going to make an arc that intersects that one, like so. And then from there, we have another new intersection here. We can call it point F. All we need to do now to bisect angle ABC is connect our vertex to that intersection there at point F, and that will cut our angle ABC in half to congruent parts right there. In our next construction, we're going to be bisecting segments. Specifically, we're going to be making perpendicular bisectors of segments. The way this works is to take our compass and put it on one end point of our segment, and we're going to open our compass so that it's more than halfway from end point to end point. Right? It doesn't have to be all the way to B. It could though, and it could go further than B, but it's easiest to make it just a little bit more than halfway. We would put our compass on an endpoint, and what we're doing is we're going to make an arc above our segment and below our segment. We're then going to keep the same exact setting on our compass, and we're going to carry it to the other endpoint. And again, we're going to make an arc above our segment. Sorry, that's been happening sometimes with my screen. Let me fix it real quick. So again, we're making an arc here above our segment, and we're making an arc below our segment. Then to create and finish this perpendicular bisector, we would just connect those intersections. If we need to, we can label intersection C, intersection D, and we would just have a segment connecting those intersections. It should be about there. It's not perfect on my screen, okay, but this would be a right angle perpendicular to this segment, and this half would be congruent to this half. So it's bisecting it, cutting it in half, and that segment is perpendicular to my original segment. Perpendicular bisector. In our next construction, we need to draw a line parallel to AB that goes through point P. This one's a little tricky, but essentially all we're going to be doing is creating congruent angles. We're going to be making corresponding angles that exist on segment AB and then also exist through point P. The way that this starts is by drawing what's going to end up being a transversal. So we're going to start below segment AB, and we're going to draw a line that goes through it and also goes through point P. So like so. Let me extend that a little bit further. Boom, that's going to be my transversal. Now notice I've created an angle down here. And this angle I'm going to copy onto point P. Okay, so if we want to, we can label this intersection down here point C. And using that as a vertex, I'm going to take my compass, and just like we copied angles before, I'm going to draw an arc that goes all the way through here. So my compass goes on point C, I'm drawing an arc all the way through. I'm going to keep this same setting I'm going to go to point P and I'm going to go below point P. So if we imagine there's a parallel line, I'm going to put my pencil below that and I'm going to draw an arc that swings all the way through and then past the transversal that I've drawn. Now we have some more points, some more intersections here, right? I'm going to label this one D, this one E, this one up here I'm going to label F, and we're going to measure from D to E. So we're going to put our compass on point D, we're going to have our pencil resting on point E, we're going to carry the same setting up to point F, and we're going to make a little arc that intersects our transversal right there, and we can call that now point G. And all we need to do now to make a line that's parallel to AB is draw a segment connecting point P to that intersection where G is. Now remember, on my screen I'm using imperfect tools. It's not going to look exactly right, but it's going to be pretty darn close. Okay, that line right there being parallel to AB. So remember, we mark parallel lines by giving them the same amount of arrows. Next, we have a similar starting point. This time though, instead of making a parallel line, I'm going to make a line that is perpendicular to AB and goes through point P. So what we're going to be doing here essentially is making a perpendicular bisector of a specific segment within segment AB. Because obviously if I bisect AB with something perpendicular, it won't go through point P over here. That would not cut this segment in half. Instead, what we're going to do is we're going to put our compass on point P, and we're going to make an opening that just passes our segment AB here. And we're going to make it just pass in a way that we can make arcs on our segment on two places here, down here. So I have my compass on point P. I'm going to swing my compass until I can make an arc over here on this side. And then I'm also going to be swinging it over here so I can make an arc on this side. And now I have 2 points that I can reference here. I'm going to label C and D, and I can cut that segment in half with a perpendicular bisector through point P. And that will create a line that is perpendicular to AB. Okay, so the way that we do this now is by taking our compass and creating arcs below. We already know point P is a spot that would be perpendicular above these two. As long as we get a point below it that is good, I can connect point P to that point. So I'm opening my compass a little bit more than halfway between C and D. I'm going to put my compass on one end point here, C, and I'm going to make an arc below, just as I did for perpendicular bisectors. I'm going to keep this same setting. I'm going to put it on point D, and I'm going to make an arc, again, below that intersects that one. And now I have, you can call this point E. I have 2 points now that I can connect from P to E that will be perpendicular to AB as I do so. So boom, going through. That looks pretty good. It looks perpendicular to me. Our last 2 constructions are how to essentially draw circles either inside or around a triangle perfectly. Meaning that inside the triangle, the edges of our circle actually hit the sides perfectly of the triangle, and then outside of the triangle, our circle hits the vertices of the triangle perfectly. This is a difficult thing to do. It requires a lot of construction. I'm going to show you just the beginning stages of it because I can't possibly do it perfect on my TV screen with the tools that I have. It will look very ugly. So I'm just going to tell you the steps that are going to be involved, and I'm going to show you by hand what they will look like. So first, we're asked to circumscribe a circle about a triangle. What that is asking us to do is to draw a triangle perfectly around, draw a circle perfectly around this triangle. So essentially, you're gonna have something that looks like this, where the circle hits all 3 vertices of the triangle. Well, the way that we do that is by finding a circumcenter, which is a point of concurrency of perpendicular bisectors. So if we want to circumscribe a circle, what we need to do is construct all the perpendicular bisectors of the sides of that triangle. Again, my tools would be very difficult to show you with, all right? But I'm just going to do it by hand just to show you roughly the process. So I want to draw a perpendicular bisector of side AB. Remember, that means I'll open up my compass more than halfway, I'd make an arc above, an arc below. I would take the same setting to point A, make an arc above, an arc below, and then I would draw that perpendicular line through side AB. And I would continue to do this for all three sides. That was side AB, then I'd move over here to side CB. I'd open up more than halfway, make an arc on one side, the same arc on the other side. I'd move the compass over to point B, make an arc here and here, and then I would connect those to make the perpendicular bisector of that side. And then again, I would do the same thing for side AC, right? So I would open up the compass more than halfway, make an arc on this side, make an arc on that side, bring the compass over here, arc, arc, and then straight edge to make the perpendicular bisector there. And then where those all meet each other would be the center of the circle that would circumscribe around this triangle. So you would put your compass there at the point of concurrency, and you can measure the pencil to any vertex, it doesn't matter which one, and once you set it there, you should be able to swing a perfect circle that would hit all of those vertices exactly around to give you that triangle perfectly inside of a circle. That's circumscribing about a triangle. Remember, you use perpendicular bisectors to do that construction. The last construction we're learning here is inscribing a circle inside of a triangle. Doing this requires you to find the angle bisectors, and where they intersect each other would be a point called the incenter, and the incenter would be the center of the circle that we're going to draw. So to do an angle bisector, we do an arc through an angle. Put the compass on one of the intersections, make an arc in the interior, take the same setting to the other intersection, arc through the interior, and then a segment connecting that intersection to the vertex is an angle bisector. We need at least one more. So I'm gonna go here at angle A, arc through, compass on an intersection, make an arc in space, same setting on the other intersection, arc in space, and then we have the angle bisector that goes through. Now from there, things get tricky for this one. What we need to know is that that incenter where these angle bisectors meet is gonna be equidistant to the three sides, which means I need to make a line that goes from that intersection perpendicular to one of our sides. And so this would be like a previous construction, drawing a line perpendicular to a segment through a point. So I would have to put my compass here and make intersections on here, and then I would need to cut this in half with a point below. So my compass would go here, open more than halfway, arc below, same setting over here, arc below. Then I would have a straight segment connecting there to there. And now the last thing I need to do is put my compass on this incenter, measure to where it reaches this side, and then I can draw a circle that would fit perfectly inside of the triangle. Again, it doesn't look perfect here because I'm using by hand on my TV screen. It's hard to do it. That is the steps though for inscribing a circle. Guys, you got this. Study hard. You can do difficult things. Bye.